All right, so this lesson is going to focus on area of a triangle, which you have known for several years is to be found by simply multiplying 1/2 times the base of the triangle times the height of the triangle. And in order to do that, you have to have a right angle somewhere, and that could be between two of the outer sides, or it could be an altitude within the triangle. So what we're going to try to do here is develop a way to solve for the area of a triangle that is not a right triangle and that does not have an altitude given for us. So it just makes the process faster if we can develop and then use this process. So just going back to sine and cosine and tangent, we've been using these trigonometric definitions the whole unit here. We know that sine is opposite and hypotenuse, cosine is adjacent and hypotenuse, tangent's opposite and adjacent. So using the sine function, we're going to develop a formula for the area of the triangle if we know two sides and the measure of the angle between them. So in other words, if we have a side, angle, side sort of labeling system. All right, so in exercise 1 in ABC, we have AC is 8, that's out here. We have BC is 12 down here. And then angle C is 56 degrees, which is between AC and BC. So if you notice, there's a side angle side labeling here, right? From the 8 through the 56 to the 12. So to determine the area of this triangle, or the height of this triangle, first off, in terms of sine 56, we're just in the development stages here. From the 56 degree angle, if I've got this altitude drawn, this little h for height is my opposite side, and the 8 would be my hypotenuse. So there's my sine ratio. So if I go sine 56, that's going to be equal to h over 8. And so in exact form, h would be equal to 8 times sine 56. Okay, so then to determine the area of the triangle and round our answer to the nearest square inch, remember area of a triangle is 1/2 base times height. Well, I knew that the base was 12 because it was given to me. And now I know the height is 8 times sine 56. Okay, so if I just type that into my calculator, I'm going to go 1/2 times 12 times 8 times sine 56. And my total is nearest square inch, so my total is about 40 square inches. Okay, so that gets us the area of the triangle without needing to know what that height was. So we can generalize this with the following formula. And so for a triangle with side lengths A, B, and C, and A is across from angle A, B is across from angle B, and C is across from angle C, we can do this by saying that the area is going to be 1/2 times little a times little b times sine of C. Now the thing that I don't care for about this formula and that I'd like to make an adjustment on here is that you don't need to have angle C particularly. You could have any angle and the two sides surrounding it. So to generalize this even further, the area of a triangle can be written as 1/2 times x times y times sine of theta. And I do want to specify where theta is between x and y. So we have an even more generalized version of it here. It could be any angle in the triangle and the two sides surrounding that angle. All right, so exercise 2, which of the following represents the exact area in square inches of an equilateral triangle whose sides have a length of 10? Okay, so let's draw that equilateral triangle. Side length's 10. We go 10, we go 10, and now a third side 10. And about an equilateral triangle, I also know that I have 60-degree angles, so we can put those in as well. Okay, and so the exact area in square inches of this triangle would be 1/2 times x times y times sine theta. And I can use any of these three angles as theta, so it's going to be sine 60. So area is equal to 1/2 times 10 times 10 times sine 60. All right, and so as an exact answer, if I take 1/2 times 10 times 10, that's going to be 50. So 50 sine 60 would be my exact answer. Now, none of these choices are in exact format, are in that same trig format. So if we look at it a slightly different way so that we can answer this multiple choice question, what if we took this equilateral triangle and split it in half? and I had a right angle, and I have a 30-degree angle now at the top. Well, at this point, the 10 on the bottom has split into 5 and 5, and you can see our 30-60 setup coming up here. So if this short side is 5, then the height here is going to be 5 times square root 3. So another way to write this would be area equals 1/2 base times height, where the base is 10, that's the whole bottom here, and the height is 5 root 3. Okay, so that would be, let's see, 10 times 5 is 50, times 1/2 is 25, so I get 25 root 3, and so that's choice 4. So there's a couple of different ways you can have an exact answer. You can have an exact answer using trig without typing it into the calculator. You can also have it in radical form. If this were not a multiple choice question, I would absolutely accept this answer as an exact trig answer, being that it was multiple choice and the format was with square roots. That's why I wanted to adjust it and go this way. Okay, on to the next page. An isosceles triangle has legs of 12 and a base angles that measure 32. So let's draw that. So we have an isosceles triangle with legs 12 and base angles of 32. We want the area of this triangle to the nearest tenth of a square inch. Okay, so remember that the area formula we just developed is for a side angle side labeling system. I don't have the base down here. I don't really have any way to get it either. So what I need to do is complete this triangle. I've got 64 degrees here, which tells me that there must be 116 left over for that vertex angle. I'm just subtracting from 180. And so now I do have a side angle side labeling system. So now I can say that the area is equal to 1/2 times x times y times sine theta, where, remember, the x and the y are the sides surrounding theta. So I can use these two 12s surrounding the 116. So I have 1/2 times 12 times 12 times sine 116. And that's just so much faster than trying to calculate the height and going through all that. So let's see, 0.5 times 144, since that's 12 times 12, times sine 116. And I'm getting 64.7. Okay, so 64.7 square inches, and that one's finished. All right, on to exercise 4. So we have AC 24, BC 30, angle C is 40, determine the area. Okay, take a second to try this one on your own. Okay, so we should have area equals 1/2 xy sine theta, and so that's going to be a 24 and a 30. And then sine 40. Okay, so we can, it's the nearest square centimeter, so we don't want an exact answer here. We want approximate. 0.5 times 24 times 30 times sine 40. And we get about 231. It wants the nearest square centimeter, so about 231 square centimeters. Okay, so using our answer from part A, determine the length of the altitude drawn from B to side AC. All right, so I need to go with a straight line from vertex B perpendicular, that looks about right, perpendicular to side AC, put a little right angle marking in there, and I want to know this length, so let's just call this x for now as a variable. Now the thing about this triangle is if I use this height, this as my height, let me actually change that to an h just to make it a little bit easier to see. It's an altitude after all, so that could be a height. And then if this is the height, then the base is the part that connects to it, where the right angle is. So the base of this triangle would be 24. If you could visualize spinning this, just rotating it, then the height would be standing up and the base would be 24. So if my height is unknown and my base is 24, that looks like the beginning of an area formula. I already know the area is 231, so let's try to solve that using area equals 1/2 base times height. So I put the 231 in for my known area. I do know the base. The base is 24, and I don't know the height. So if I just, this 1/2 of 24 is 12. If I just divide 231 by 12, I'm getting 19.25. So that's just another way to make use of the area formula. We have the altitude now drawn from B to AC. Okay, so moving on, exercise 5, the last exercise in the set, and you can try this one on your own, draw a good diagram of it, and then we'll see how you did. All right, parallelogram garden. Kind of a strange decision. But we have a parallelogram garden, and that's not the nicest looking parallelogram, but you get the idea. In fact, I'm just going to cheat and get a good one here. So let's get a better parallelogram. Yeah, I'm going to be happier with that. So, okay, so now the information tells us we have acute angles of 45 degrees. And we have sides of 40 and 30. So we'll go 40 here and 30 here. Okay, and we want to know the area of the garden. So we have a couple ways we can go about this. We could dissect this parallelogram and create a rectangle within it. We could use the formula for area of a parallelogram, which is base times height. And if we do that, then we would be thinking about having to solve for one of these dotted blue lines to get the height of the parallelogram. We could possibly split this parallelogram in two. And I'm just going to do it this way, and you'll see why in just a second. So if I split it that way, now what I've developed is a triangle with a side, an angle, and a side, and another triangle with a side, an angle, and a side. Whoops, got those backwards, 30 and 40. So I think, given all my options here, I think this is going to be my best bet, because if I just do 1/2 xy sine theta, I can just do that twice and get the whole parallelogram. So I'm going to do 1/2 times 30 times 40 times sine 45. And then since I'm doing that twice, I'm just going to ignore the 1/2, because multiplying by 2 would negate that. So 30 times 40 times sine 45. And I'm getting 848, and what's the nearest square foot? So 849, about 849 square feet. And again, you could have done it with these blue lines. You could have easily solved for this, because you would have had a right angle, which is a 45, 45. Could have divided 30 by root 2, gotten your height, and then used that along with the 40 base, and you would have gotten the same result. Just seemed, given our new formula, that this was a good way to do it, because by splitting it this way, I have my side angle and side. Also note, if I had split it the other way, since a diagonal does not bisect an angle in a generic parallelogram, only does that in a rhombus, I would not know how that 45 was split, and then I wouldn't have any angles at all. So that's why I wanted to split it this way, to make sure that that 45-degree angle stayed intact.